morning. I think we will first recap what we did yesterday. We talked in terms of the explosion being defined as something which makes a loud noise, a loud bang, which is followed by disruption of things in the zone of the explosion. Like for instance, I have an explosion over here. What happens is it not only makes a loud noise, but also it disrupts the things at the zone of the explosion, in and around the zone of the explosion. Why did it happen? We talked about sound waves. We said, well, the sound wave propagates through a series of compression and rarefaction, maybe small compression rarefaction about the mean value. Let us say these are pressure perturbations. Any pressure perturbation is associated with a temperature perturbation. We related the temperature perturbation with the pressure perturbations which are there in a sound wave. We also find that there are velocity perturbations in this, and the front propagates with a sound speed a0 in the case of sound, which propagates as a sound wave. Now, what happened was, we told ourselves when the amplitude of these motions are large, like for instance I have a large amplitude which is created by some energy being deposited at this particular point, which is sort of more instantaneous. I have a larger amplitude. What happened was the sound speed wherein at the crest of the wave wherein the pressure perturbation is high with the associated temperature perturbation is high, we found out the expression, the sound speed is given by under root gamma, which is the ratio of specific heat into the specific gas constant into the temperature, and therefore, at this point wherein the temperature is higher, you have the sound speed which was larger. Here at the crest wherein the temperature is lower, I have the sound speed which is less than the mean value. Here it is mean, and therefore, this wave became somewhat steeper, and ultimately it became something like a shock wave. This is what we called this wave, which was a steep wave, as a shock wave, and it increased the pressure from the ambient pressure, let us say P naught, to a higher value, let us say delta P. Therefore, this is what is there, and what happens behind it? You have the trailing of the wave behind the front, and this I can now represent as, let us say, well, the instantaneous release of energy at a point creates a shock front, and behind the shock front, well, the pressure has to go back to ambient, and I have something like a rarefaction wave, that is an expansion fan behind it, and this is what created a sudden pressure rise which we felt as a loud bang. Now, what happens? Let us put some more time on it. Let's spend some more time on this problem. You know, you have a pressure rise taking place, and we also found that because now the events are not gradual, in this case the change in pressure is very small, and therefore it could be reversible. We also found that air being somewhat of an insulator, it does not transfer energy, it does not take the amplitudes are small, then the air being an insulator, the process is adiabatic, there is no heat transfer taking place, therefore, the propagation of sound wave is isentropic. But the moment I have a large amplitude and a steep rise in pressure, the events are not gradual but sudden. I have large gradients in temperature, in velocity, in temperature, in velocity, and again you have in pressure, and therefore, these gradients lead to heat transfer effects, lead to shear effects, and therefore, because of heat transfer and shear, some of the energy gets dissipated in the particular wave. In addition to the energy getting dissipated, if I were to plot this figure again, what is it I get? I get, well, what has happened is because of the instantaneous release in energy, I get a steep fronted wave. This is the ambient pressure, and this is the expansion behind it. This is, let us say, the front of the shock. Anything sudden is a shock. We found that it travels at speeds greater than the sonic velocity, namely supersonic speed. I have expansion behind it. The expansion is what we call as a rarefaction, and now the temperature is higher. With the result, the rarefaction which moves behind the shock, it moves faster than the speed of this. Originally, if it is ambient pressure, well, it is 330 meters per second. If temperature is higher, rarefaction goes faster, and therefore, what would happen? Let us try to plot it again. Since it moves faster, as the wave progresses further, well, the wave progresses further, it goes through some distance, I have the expansion fan progresses faster, and therefore, the amplitude of the front now decreases. As it progresses further, it catches more and more with the front, and therefore, what happens is the wave catches in front, and therefore, the amplitude of the front decreases, and ultimately what I get is the expansion fan like this. It has moved a further distance over here. Let us plot it over here. It has moved a further distance over here, and therefore, you have this, and the expansion fan comes over here. Now, with the result, the amplitude of the wave motion which is built up, or the pressure rise across the front, which is compression, keeps progressively getting decreased. And what did we tell ourselves? Well, in addition to dissipation of the dissipation in energy due to heat transfer, due to shear, what happens is now we also have, because of the rarefaction fan coming in contact with the shock wave, the strength of the shock wave keeps decreasing, and ultimately what is it we get? We get something like, let us plot it out with distance x. We had the streak diagram. We had for a sound wave, well, this is the speed C naught or A naught at which the sound is propagating, typically around 330 meters per second in ambient conditions. Now, what is happening? Initially, I got a wave which started at supersonic speed, and then the amplitude keeps decreasing, that is, the velocity keeps decreasing, and ultimately it becomes something like this. That means, initially I start off with high speed and the velocity keeps decreasing until it becomes a acoustic wave in the limit. Therefore, in the near field, that is near to the source which release the energy over here, I get a shock wave which subsequently becomes something like an acoustic or a sound wave in the very far field. Therefore, this is how it looks like. If it were a shock which is supported by the energy release, maybe if I have a constant velocity shock, maybe it would have gone straight like this. But because the rarefaction fan catches up because of the dissipative effects, and once the energy is released, there is no energy to drive the shock front, it dissipates, and this is what we call as the blast wave. We also told ourselves, because the pressure is continually changing, when pressure changes, well, I have the velocity which is changing, I have a wind effect, therefore, I have huge wind which we call as the blast wind, and this is what is the genesis of a blast wave. We can take a typical example. Let us say we have lightning taking place. What happens? When lightning takes place, if you are very near to the source of lightning, I get a loud bang, I hear a loud bang as it were. But if I am far in the far field, I do not hear that huge thunder or bang, but what I hear is the rubble associated with thunder, some sort of a rubble associated with thunder is what I hear. And this is what is maybe in the far field I hear a continuous drolling noise, in the near field I hear a huge bang, and this is what is the signature of an explosion taking place. This is what we did yesterday. Now, let us go forward. Let us try to see whether I can still define my explosion in a more detailed way, in some way which is stronger. Let us say I would like to model it also, I would like to see what are the controlling factors. Can I redefine explosion in a slightly different way? All what we said is, we can now say when a blast wave is formed by energy being released at the source, somebody releases some energy at the source. If a blast wave is formed, we said, well, it is an explosion. Therefore, now we tell ourselves, well, conversely, I can also define an explosion if energy release at the source is such that a blast wave gets generated, then I call the energy release to be explosive. That means, I indirectly tell myself, if a blast wave gets generated by some sort of energy release, and let us say this energy release is E naught joules at some particular place, and if I am able to get a wave we defined the wave, we said wave only transmit or carries the energy from the source, it does not physically carry the material from the source into the wave, and this is how we defined a wave. And therefore, we say if the energy release at the source is such that it creates a blast wave, well, we can say an explosion takes place. As per the parlance or as per the definitions, normally this energy release must be fast or instantaneous. What do you mean by instantaneous? Well, let us consider one or two cases. Let us say, well, this is my axis, this is the distance x, and now or let us say I am looking with respect to time, because I am looking at the instantaneous with respect to time. Maybe I deposit some energy, I start deposition of energy and I finish the deposition of energy here. The characteristic time of energy release I can define by, let us say, the tau over here, this is where the major amount of energy gets deposited. And now, if the time tau, that is tau seconds, over which the effective energy gets released, tends to 0, well, I say, well, the energy is released sort of instantaneously, and what happens? A shock wave or a blast wave gets generated, and this is how the blast propagates out. Now, if the energy release is more gradual, what would happen? Let us take a look at that scenario. Maybe I tell myself again over here, maybe this is my time, this is my value of the energy, total energy which is released, and here I say the rate, this is the rate of energy release, this is the integral behind it is the total energy release over here, this is so much watts or joules per second. When I take the energy release to be such that it is gradual, you know what happens? Like yesterday we had the example of a flute. Let's repeat this example, because if we are clear about the basics we can go forward in any direction. What did I do? I blew into the flute over here, and when I blow into the flute I do have some kinetic energy which is getting released, and this is the type of energy which is getting slowly released in the system. Now, instead of this I also showed you the example of a balloon. Maybe I have a balloon, I blow air into it, I consider now I store some energy here, namely the potential energy over here, and all of a sudden when the membrane bursts, what happens is the stored energy is released over a very small time, and this is how the energy gets released over here. Now, when I gradually release the energy, it appears to me like a sound wave, and even if the magnitude of energy release is high, if I were to get the magnitude of energy release to be high, and if I am able to form something like a blast wave from it, what is going to happen? The continuous release of energy in this zone is going to continuously drive my blast wave. That means the blast wave is driven by the energy source even after formation. Therefore, it is something like a piston driven blast wave, something like I keep on pushing the blast wave. In other words, if I were to now plot the value of, let us say, on the streak diagram, t versus rs or t versus the distance x over here, I have in one case the blast wave being formed over here when the energy release is instantaneous. When I keep on providing more and more energy, well, the blast wave will get affected, and this is the type of blast wave which I get. Therefore, whenever I have a slow release of energy, well, what is it? I get a sound wave. If it is instantaneous, like sharply taking place, and it falls down, well, the energy release is so spontaneous that it drives the blast wave, and once the blast wave has taken off, the energy release is 0 and the blast wave is on its own. Therefore, these are the three things, and this type of a situation wherein the energy release tau, the period of energy release tau is such that it tends to 0, or rather in this case I have dE by dt, t tending to 0 tends to be infinite, is what we call as an idealized explosion, because once the energy release is given, the shock wave or the blast wave which drives it is on its own. Therefore, we must learn the difference between an ideal explosion, which is something wherein you have the energy release taking place over a short period of time, you could have a piston driven type of a solution in which the energy release continually drives the blast wave, and if the energy release is small over prolonged period, I get something like a sound wave. Having said this, let us also be clear about the mode of energy release. Well, the mode of energy release need not always be, as we said, in a particular volume. This volume could be a point maybe, or it could be a sphere, in which case I get something like a spherical wave which originates from it. Maybe at time t1 the wave is over here, as time increases the wave comes here, it keeps on. I could get a spherical shaped wave from a point or a spherical geometry over here. If I consider something like lightning or something like a discharge which takes place in a line, that means I have, we would have observed lightning taking place in the sky. What happens is all of a sudden there is a line discharge, that means I have energy being released in a line. What is going to happen? Well, the blast wave is going to propagate along this in the case of as a cylinder. Therefore, I could have in the near field something like a spherical one which propagates out. In the near field, I could have something like a cylindrical wave which propagates out, and in the limit I can also imagine if the energy is released in a plane, let us say something like this, and what is going to happen? I could have something like a planar blast wave which moves out. Therefore, I could have different types of waves, namely a spherical blast wave, maybe a cylindrical blast wave, and a planar blast wave. These are the types of things we could say. We could have, let us say, a point explosion or a spherical explosion, a cylindrical explosion, and a planar explosion. Therefore, this is all about the introduction to explosions, but let us try to go forward. What is the problem we are considering? We would like to have a knowledge of how this blast wave propagates, what is the type of damage it does, because our interest is one, to prevent an explosion, and if an explosion takes place, how to mitigate the effects of the explosion. For that, I have to first understand the physics of the explosion. Therefore, let us say, well, I deposit some energy E. Let us also assume that this energy deposition is instantaneous. Therefore, I have dE0 by dt tending to infinity. That means I just deposit it. My characteristic time tau over which the energy is getting deposited tends to 0. Then what is it I am talking of? Well, what is it I have done? We have deposited some energy in a small volume. Let us for the present consider a spherical symmetry, and then what is going to happen? Well, I have a spherical wave which propagates out. Maybe at time t after the energy is deposited, namely the energy gets deposited over a time t, and I am interested maybe at what is the type of the radius. This is the radius of the blast wave. What is the distance from the center at time t, namely I am interested in this. Let us call it as radius of the shock wave at this particular time at time t. That means a wave gets originated maybe at a larger time, the wave is over here, and therefore what is the conservation I do? See, I deposit some energy here, and this energy could be potential energy because I am depositing some energy here. And what is the potential energy I have? We know, yes, potential energy is the energy, or let us say associated with the internal energy of your system, and it is equal to, for per gram of the substance, it is equal to specific heat at constant volume Cv into T minus T0, wherein T0 is the ambient condition. That means it has an excess energy for per unit mass corresponding to this. Therefore, per unit volume I multiply by density of the medium into Cv into T minus T0 is the excess energy contained over here. Therefore, therefore, this is the potential energy which is deposited. Now, what is happening? I have wave motion, I have velocity of particles behind it, and therefore, this potential energy gets partly converted into kinetic energy. And what is this kinetic energy per unit volume? It is equal to rho into V squared divided by 2. Per unit mass it is V squared by 2, per unit volume it is this, and therefore, the energy which is released in the source as potential energy gets continually converted into kinetic energy and part potential energy, and therefore, I tell myself, well, the total potential energy is locked within this, because outside this the effect of the wave are not there. This travels at supersonic speed. Well, the medium outside is not affected, only the medium which is enclosed by the lead blast wave or lead shock wave gets affected, and therefore, if this volume is V, the total potential energy in this medium corresponds to rho Cv into T minus T0, so much joules, and the kinetic energy enclosed by the lead shock wave is equal to integral over the volume into rho into velocity square divided by 2. Of course, I have dV here, dV over here. Well, this is velocity, this is volume, maybe I should have written this as small v for volume, and this is the velocity over here. Therefore, what is happening? The initial potential energy which is there gets conserved into the potential energy in the total medium, which is now lower, which is now spread out, and the kinetic energy in this medium, and therefore, if I can imagine in the far field very far away, what is going to happen? If I were to neglect the effects of dissipation and also the effect of rarefaction catching the shock wave, I can tell myself, well, this the total energy, mainly potential energy and kinetic energy, which is equal to the initial potential energy in the medium, is sort of conserved, and therefore, this energy is unique to an explosion. That means, in the far field I can still characterize my explosion in terms of the total energy which is given. We will look at this a little later, but let us keep this point in mind and proceed further. We tell ourselves, well, the energy is conserved. Can we make any more guesses, or can we talk in terms of the problem in some more detail? Let's try that. Let us now take a look at this energy which gets conserved over here. You know, I tell myself, well, the total energy gets conserved, and what happens if the energy release is instantaneous? What happens if the energy release is a little sluggish? Therefore, let us again plot over here time versus the rate of energy release. In one case, the energy release is very fast. In the other case, maybe the energy release is fast, but over a slightly prolonged duration. In the first case, well, this is my characteristic time tau 1 of energy release. In the second case, the energy is released maybe over a slightly effective energy release over a time tau 2 seconds. Now, this is the second case. Now, when the energy release is a little slower, the net energy release is, let us say, in both the cases is obviously different. Maybe if it is same, maybe the peak should have been a little lower. But what is going to happen in this case? In the second case, maybe because of diffusion of energy, the ambient gets heated, or rather, whenever I have energy release and the medium gets heated, what happens? The medium gets heated, and if the medium gets heated, the medium is no longer isentropic. Rather, I cannot have the isentropic because now I have heating. Therefore, it is a case wherein, not being adiabatic, I am going to have some wastage. That means, the temperature rise is not going to contribute to my front over here, and this temperature waste becomes sort of my waste energy. The energy from the release goes into heating the medium, and when it goes into heating the medium, it does not contribute to drive my shock wave, and therefore, we say a slower energy release is not as effective as a fast energy release. Well, these are the preliminaries. Now, we go into modeling it, and when I try to model it, let us try to model it for a simple situation. Let's see how to go about it. You know, in the problem that we are considering, we have energy release at a particular point, let us say over here. The energy release we say is instantaneous, and what happens? Well, at time t I have a shock front, and let us say it has a spherical symmetry. At time t I have a shock front which is at a distance r(s) from the center of the source. Let us also assume that the size of this source is so small that it is a point. Therefore, we have point source, which releases energy instantaneously, therefore, the time of energy release does not come into the picture, because the blast wave is on its own once it is created. The size of the source does not enter the picture because it is a point solution. We call it as an ideal case of an explosion. Well, at t seconds, the shock wave is at a distance rs meters. Why is it formed? We have an energy release E naught joules at the source, and what is the parameter of the surroundings which influence it? Well, the density of the medium, let us say rho naught, because it identifies air or any other substance which is there. Therefore, rho naught is the density, so much kilogram per meter cube, which for air at ambient pressure is around 1 kilogram per meter cube, and these are the parameters which define it. Therefore, I tell myself, well, I am interested in finding out the strength of a shock wave or the blast wave which is formed when I deposit energy E0 joules, and I want to find out the distance travelled by the shock at time t, because if I can find out an expression between distance and time, I can always find out the velocity, since I know the dependence of rs on time as a function of time. I can always find out d rs by dt, which is the velocity. Therefore, I want to do this problem, but when I want to do this problem, I find, well, the problem is not as simple as it sounds. The reason being, well, the shock wave is moving, it continually processes more and more of the ambient air, point 1. Second is, well, the kinetic energy, potential energy behind it are continually changing. Well, it is totally unsteady problem, totally unsteady and transient problem, and to be able to do this problem, to be able to write the continuity, momentum and energy equations using which I solve this problem is going to be complicated. We will do it a little later, but can I do it in a simple way? You know, all of us, when we started with our engineering education, we start with something known as a dimensional analysis and what we call as the Buckingham Pi Theorem. Let us see whether I can use dimensional analysis to do this problem, because I keep repeating this in all the other classes also, because the dimensional analysis gives you a good feel for a problem when the problem is complicated. Therefore, let us use the Buckingham Pi Theorem and see whether I can get some idea about this problem. In fact, at this point I must also tell you that this dimensional analysis and getting a feel for blast wave was first done by G.I. Taylor in 1950. The genesis of the problem was the following. You know, in 1945 we had, I think it was in August 1945, at the end of the World War, that was when 2 bombs were dropped over Hiroshima and Nagasaki. I think it was August 9, 1945. And what happened? It was a catastrophe. It killed a lot of people, it maimed people, and the radiation effects were felt for a very long time. But the energy which was released from the bomb was not known to anybody. And what G.I. Taylor did was, he analyzed the problem using dimensional analysis, and he was able to precisely point out what is the type of energy which got released in the bomb. Mind you, the thing was kept confidential, it was not open, it was classified, but even then, using some data which we will now see, Taylor was able to do. I would strongly urge all of us to look at this paper. I have this reference here with me. Well, the reference is, the title of the paper which G.I. Taylor published was the formation of a blast wave by a very intense explosion. As I said, it appeared in 1950 in the Journal of Proceedings of Royal Society, London. It came in the mathematical and physical series of these proceedings. The volume number is 201, It is between pages 159 to 174. It is available on the net and it is a beautiful paper. I would strongly urge you to read it. It gives you a feel for how to go about doing the dimensional analysis, which we will now do. Having said this, let us go back and try to see how we do the dimensional analysis. We told ourselves, well, we have the energy getting released E0 joules. We want to find out the distance the shock wave is from the source at time t seconds. The shock is propagating in a medium of density rho. Well, RS is in meters, time is in seconds, density is in kilogram per meter cube. Let us put the dimensions together. Joules is force into distance Newton meter. What is Newton? Newton is equal to kilogram meter per second square meter. Therefore, it is equal to kilogram meter square by second square, that is the unit of energy. Well, R0 is meters, T is seconds. Well, this is kilogram per meter cubed again. If I were to put this in terms of the dimensions, well, dimension of meter is length scale, linear distance, mass is m, time is t. Therefore, I could say that the joule energy has units of m L square by t square. The unit of RS distance is equal to L over here. The unit of time is t, t is the unit of time. Well, rho has units of m, that is mass divided by L cube. Therefore, you have the dimensions of energy, distance, time and rho as is given. And now, using the Buckingham Pi theorem, we find, yes, we have something like 4 parameters here. And now, out of these 4 parameters, I find 3 of them have independent dimensions. That means, I have 4 parameters in my problem, E0, RS, T and rho, of which 3 have independent dimensions, because I am able to relate, maybe time is independent, length is independent, I am able to relate, if I have one more, I am able to get the other dimensions out, 3 independent dimensions. And as per Buckingham Pi theorem, if I have 4 parameters and 3 independent dimensions, I can form one non-dimensional parameter. Let us get this value. Let us say the one non-dimensional parameter we call as pi 1. Therefore, I want to find out this non-dimensional parameter. I have, let us say, this non-dimensional parameter is pi 1. Well, it is a function of distance, energy release, maybe the density, maybe the time. And if it has to be non-dimensional, well, I can write it as equal to, I am interested in RS, E0 to the power A, rho 0 to the power B, time to the power C, such that A, B, C and the factor 1 are so chosen such that the net dimension of pi 1 does not have any dimension, it is dimensionless. Therefore, what I do, I immediately put the dimensions of this into this figure. Well, I get L over here, E0 is equal to m L square by t square to the power A, rho 0 is m by L cube to the power B, t to the power C. And now, in order to get non-dimensional, let us put all the L together, all the m together. I have L into 1 plus 2a minus 3b, then I have m is a plus b, and t is minus 2 plus c is equal to the pi 1. And if this have to be dimensionless, well, 1 plus 2a minus 3b, that is 1 plus 2a minus 3b must be equal to 0, a plus b, the dimensions of m must be 0, a plus b must be 0, and minus 2 plus c should be 0. Let us therefore get the equations clear. Therefore, I have 1 plus 2a minus 3b equal to 0. I also have a plus b must be equal to 0 to get a dimensionless number, and minus 2 plus c minus 2a. I am sorry, it should have been 2a. I have 2a minus 2a plus c equal to 0. Let us solve these equations. From the third equation, I get c is equal to 2a. I also get b is equal to minus a. Therefore, I put it in the first equation. I have 1 plus 2a, 1 plus 2a. Now, 1 plus 2a minus 3b is equal to plus 3a equal to 0, or rather I get a is equal to minus 1 by 5. If a is equal to 1 by 5, well, b is equal to plus 1 by 5, and the moment I say this, c is equal to 2a, that is equal to minus 2 by 5 over here. Therefore, my dimensionless number pi 1 now becomes, let us put it together, let us go back. My dimensionless number pi 1 is equal to Rs into E 0, A is minus 1 by 5, then I have rho 0 to the power b, b is equal to plus 1 by 5, and I have t, t is equal to minus 2 by 5, and this is the expression I get for the dimensionless number. Now, for a particular value of the dimensionless number, I can now write the value of Rs is equal to, for a particular value, constant value, let us say c of the dimensionless number, I have c into E 0 to the power 1 by 5 divided by rho 0 may be, I put this both together, into t to the power 2/5. Now, therefore, I find that the distance at time t in a medium of density rho 0, when the energy released is E 0 sort of instantaneously, the shock distance Rs is given by this particular expression. For a given value of energy release and for a particular medium, let us say the blast wave is propagating in air, well, this becomes a constant. I can write Rs is equal to a t to the power 2 by 5. What does this expression tell us? Let us try to plot it out, whether whatever we have been discussing earlier, whether it fits in. All what we are saying is, when I plot Rs as a function of time, well, as time increases, the distance Rs increases, but if the exponent was 1, well, I should get a figure like this. If exponent was greater than 1, well, it should be like this. Now, the exponent is less than 1, therefore, the shock propagates out like this. In other words, in the initial phase, for a given incremental time, when time is small, the shock propagates a larger distance, whereas at the end, maybe at a larger time, for the same incremental time, the distance travelled by the shock is smaller. Rather, if instead of putting it in this figure, I put it in the form of the streak diagram which we put earlier, namely t over here, the distance Rs along this, well, I get the figure like this, which is what we thought initially. It starts off at a high velocity and ultimately it becomes an acoustic wave. Therefore, this dimensionless analysis has been able to give you the type of the radius of the shock at a time t, and now using this, let us go ahead and do some more analysis before we discuss the results again, and also discuss the results how Taylor was able to guess the energy release in the bomb explosion over Hiroshima and Nagasaki. Let's tell, yes, we have the expression Rs is equal to AT to the power 2 by 5. Therefore, I am interested in the velocity at which the shock is propagating. I have dRs by dt, which I say is Rs dot. I do not want to carry this differential, I denote the velocity by Rs dot dRs by dt, which is equal to 2 by 5 a t to the power minus 3 by 5. I differentiate this, and now I want to express the velocity as instead of as a function of time, as a function of distance, and therefore, I can now write this as equal to 2 by 5 a t to the power minus 3 by 2, or let us say 3 by 2 over here, into I would like to somehow bring this into the picture. Therefore, I say, well, I want Rs over here, I write it as 2/5 into to the power minus 3 by 2 over here. Now, I introduce a value of a over here, and therefore, I divide this by a to the power minus 3 by 2 over here, and therefore, what is it I have? I have 2 by 5 into, I have a over here, I have constant over here. Well, I can put it as something like this particular value, I call it as b, and a t to the power 2 by 5 is nothing but Rs. Therefore, I get Rs to the power minus 3 by 2 is the value of Rs dot. In other words, what does this tell us? Well, I have the shock propagating along the radius or along the distance Rs over here. It starts off with a particular velocity and it keeps decaying down according to this particular expression. That means, this is Rs dot over here, and this is all what we said. It starts off with a high velocity and keeps coming down, ultimately it becomes an acoustic wave. Therefore, we find that yes, using dimensionless analysis, I am able to get the value of Rs, I am able to get the value of Rs dot, but now getting back, how can energy of, how could Taylor determine the energy release in an explosion using this dimensionless analysis? Let us put things together again the one last time. We find well, Rs is equal to C E0 to the power 1 by 5, rho 0 to the power minus 1 by 5, and T to the power 2/5 over here. This is the expression what we derived. You know, in these old cities of Nagasaki and Hiroshima, you know, in these older cities and all that, we find these clock towers which are there. And due to the explosion, when the blast wave hits a clock tower, the clock stops at a particular time. Let us say there are two clock towers separated by a particular distance. This stops at a time t1 when the blast wave hits it. When the second blast wave hits the second one, let us say it is at time t2. And therefore, the time of these two towers, the clock towers are known, and therefore, I have the distance between them is known. Therefore, the only variable is the energy over here. I know the ambient density over here, and using this, Taylor was able to get the value of E0, and it came out to be something like 40,000 tons of TNT, or in terms of energy, it is almost like 100,000 megajoules of energy. I do not clearly remember this, but we will study the equivalence of energy in terms of explosive. We express it in terms of TNT, which we will do later on. Therefore, this simple dimensionless analysis shows the characteristics of the wave, namely the wave decays out as it progresses faster. It starts strongly, as we say here, starts strongly, progresses over here. Can we also make some predictions for, let us say, the rate of decay of the blast wave? In other words, what is it we are saying? Well, it decays out. I know the value of Rs dot, and we said Rs dot is equal to B Rs to the power minus 3 by 2. Can I get its deceleration, that is the rate of decay? In other words, I am looking at d2 Rs by dt square, which is equal to d Rs dot by dt, and therefore, I differentiate this expression again. I get this is equal to minus 3 by 2 b of r s to the power minus 5 by 2 into drs by dt. This gives me the value as equal to minus 3 by 2 b r s. I can write it as minus 3 by 2 into I now write, yes, I have r s to the power 3 by 2, therefore, I have r s to the power, I write it as minus 1, therefore, it gives me 5 by 2 again into r s dot again. Therefore, what is it I get? Can I now write the value of the deceleration, which, well, this is equal to r s 2 dot. Now, I already know that the value of b r s to the power minus 3 by 2 is equal to r s dot. This is equal to r s dot over here. Therefore, I can write it as minus 3 by 2 into r s dot over here, r s dot over here, it becomes r s dot square divided by r s, and therefore, I find that the value of r s 2 dot into r s divided by r s dot square is equal to minus 3 by 2. Therefore, I get the value of the deceleration, and I find, well, r s dot is the velocity which is positive, r s is the distance, and as I progress r s is positive, and there is a decay, and this is what we say a blast wave continually decays in its velocity as it progresses. This is r s dot as a function of r s, or in terms of a streak diagram, maybe t versus r s starts with a high velocity and ultimately becomes a acoustic wave. Well, this is what we learned from dimensionless analysis, and therefore, this dimensional analysis is quite strong. It gives some suggestions, but what are we really interested in? I think let's spend a moment or two on this. See, we are interested in finding out the blast wave which is generated from an explosion, and it is this blast wave which sort of equalizes or maybe takes the source energy and distributes it over the region enclosed by the lead shock. That means, we had the explosion taking place over here, we had some energy E naught, this energy is sort of redistributed in this is done by the lead shock over here. And what is it we are wanting? We want to know what is the damage which can occur by this particular wave. We know that the matter here is not coming over here, it is only the energy which gets redistributed. We would like to know, well, when I have a wave like this which is coming, I would like to know what is the overpressure, what is the pressure with which, supposing somebody is standing here, he gets hit by the wave. What is the type of overpressure which hits him? That is, there is suddenly a compression which really squeezes him. That means, there is an overpressure which affects him, and also in addition to the pressure rise delta P which affects him, there is also behind it, there is something like the pressure falls. We saw this, we found that an N wave is like this, we found that the pressure keeps falling. Therefore, what are the two factors, or what are the factors which we must consider when describing a blast wave, to be able to quantify how the source energy affects from the explosion affects the building or whatever it is a little bit away from the site of the explosion. Therefore, to be able to do that, let us put two things together. One of the factors we said is, well, you have a shock wave which is formed, this is the ambient pressure P naught, you have a rise in pressure delta P. This overpressure is what we call as delta P, the pressure over and above the ambient, this is the shock pressure Ps, Ps minus P naught is equal to delta P, which literally crushes whatever is in the path of the blast wave, and this is one factor which we must consider. That means, we say overpressure. Now, let us try to imagine this slightly. I want to introduce another definition. Supposing there is a source here wherein some energy gets liberated and a blast wave is moving out. Well, I stand away from this and I just look at the way the blast wave is progressing. Let me try to put it in a slightly different way. Supposing at this point there is an explosion and some wave is propagating out, I stand away from the explosion and see how the waves are looking. That means I get an end view of the explosion. And how can I sketch it? Let us try to sketch this. Let us say I have an explosion taking place, a wave, shock wave travels out. Maybe I am standing away from this and I am looking at the end view of how the shock is propagating. What is it I see? Well, initially if I were to look at the pressure dependence and I am looking as a value of time, maybe at time, let us say at time t, the wave comes at this particular point. I am interested, I am concentrating on at this particular point. At this particular point, initially the pressure is ambient pressure. Let us say I show the ambient pressure in red. Well, after the explosion has happened, at maybe at time t a, this wave comes at this particular point. I am focusing my attention standing away from it. At this particular point I am concentrating. When the shock comes over here, I get an overpressure which is delta p. The ambient pressure rises from P0 to Ps over here, and as time progresses the wave further travels away. When the wave further travels away, I am left with the rarefaction fan behind it, and therefore the pressure keeps falling. The pressure keeps falling. Well, it may reach the ambient value, or if the momentum is sufficient, it can drag it and give rise to a negative value of pressure, but ultimately in long time I have this. Therefore, the end view of pressure at a particular point, let us say A, when I look at the sequence of wave propagation, is something like a pressure spike when the time of arrival of the shock wave is T A. Maybe it reaches the ambient at a time, let us say T A plus T plus, this is the positive value of pressure, and then I get a zone of negative value of pressure. I have T A plus T plus by plus T minus, this is the region of T minus, this is the region of T plus. Therefore, I find, well, this is the type of pressure distribution what I must get. See, we said, well, there is overpressure delta P, which we said will crush the object, and now this varying pressure will result in a wind or something like a momentum. And how do I get this momentum? Well, we tell ourselves, well, I want the change in momentum due to the wind effect, and the change of momentum, if I say, well, change of momentum is what we call as impulse. Impulse is change of momentum, and now the rate of change of momentum is equal to force. Therefore, and what is the force? If I have a frontal area, which is, let us say, area A is the frontal area, and if I were to take a look, well, pressure into area is equal to force, and therefore, I can tell that rate of change of momentum, that is d by dt of the momentum change, let us say P is equal to the force, which is equal to P into A, and therefore, now rate of change of momentum, I should have used a different notation here. I say mv is the rate of change of momentum is equal to pressure into the frontal area, or rather this particular expression, now I can say the change of momentum I can say is equal to integral of P A into dt, because this is d by dt is this, or rather I can say the impulse or the change of momentum associated with this particular expression is equal to the value of the higher pressure, that is P at any time. That means, I say the impulse positive is equal to the area, because I have area which is, I say, is constant frontal area, into something like P at t minus the ambient pressure into dt over the time between the arrival of the shock at time t a to the time t a plus T plus over here, and similarly I get a negative impulse or momentum in the opposite direction, which is equal to A into T A plus T plus. This is where I get this particular point. I have T A plus T plus T minus into I get P T. I now get the value, this is lower, therefore, I should get the value of P 0, because I am talking in terms of negative impulse, minus P t into d t over here. Instead of looking at the area specifically, I can say specific impulse, that is impulse per unit area, I can write as this value, I can write negative specific impulse per unit area as this, and it is this which gives me the blast loading due to wind, and therefore, a blast wave is characterized by the crushing pressure, that is the overpressure, and these two positive and negative impulses. We will see that these positive and negative impulses there could be a series of them, we will take a look at it. Therefore, what we would like to predict is, we would like to predict the overpressure and the impulse in an explosion to be able to proceed further, and this we will do a little later. Therefore, what I do in the next class is I continue on this, but before we start describing a blast wave, predict the overpressure, predict the impulse and see the effect of the damage, what we will do is we will try to take an example of some of the naturally occurring explosions, some accidental explosions, some intentional explosions, such that we are able to relate the physics of explosions with the different explosions as occur in practice. Therefore, in the next class, what we will do is, with this background, what we have built on explosions, namely a loud bang and disruption of things, looking at the blast wave and blast wave which keeps decreasing in strength, that is a decaying shock wave, and the effects like through dimensionless analysis, we were able to find out the velocity, the decaying, and also something like overpressure delta p, the impulse what we have. With this background, we will examine the different types of explosions, some typical explosions in 8 categories, and then after reviewing the different types of explosions, we will go back and try to predict the overpressure, impulse, and proceed further. Therefore, we meet in the next class, wherein we will take a look at the different types of explosions, the different categories of explosion, which we said in the last class was divided into 8 different categories. Well, thank you then.